Hello, oceanography students. Today's video is going to be on the different parts of our ocean. Uh, an individual ocean is basically an ocean basin filled with water. Okay, so today we're going to talk about the different parts of the ocean basin, or kind of the sea floor and the features that exist at each of those. And then the next lecture that you'll watch, we'll talk about the different types of sediments that exist in those different features along the seafloor. Okay, so there are basically Earth is made up of continent and ocean. Okay, so Earth consists of two physiographic provinces, continental platforms and ocean basins. And these two areas, land and ocean, are connected by a region of the ocean that is referred to as the continental margin. Okay, and we'll talk more about the continental margin in just a little bit. So if you look at this image, on the left side of the image, we see a graph that is showing us the percentage of Earth's surface that is made up of either land on top and ocean on the bottom, and the average height of land here and what the percentage of each is at different height. And then down here is the percentage of ocean that is at different depths. Okay, so it should stand out at you that land, the majority of land is between 0 and 1 kilometers tall. Okay, the majority of the ocean is between 4 and 5 kilometers deep. Okay, so ocean depth on average is almost 4 kilometers deep, so it's 3,729 meters. Over here is showing you more of a visual depiction of that. So we have Mount Everest, the tallest mountain, and then we have the average elevation of land, which is only 840 meters. And then we go to the continental margin, which is now we're underwater and we're in the ocean. Okay, and we go into different parts of the ocean. We have the continental margin, then we have the deep ocean, and sometimes we have trenches in those oceans, which are extremely deep scars in the seafloor. And this down here is showing you the percentage of that. So if we go to land and we go straight up, we see that land only makes up about 30% of our Earth, whereas 70% of our Earth is made up of ocean. Now, land consists of two different types of crust. If you remember from our previous lecture about the different layers of our planet, the surface layer, the outside layer, is called the crust or the lithosphere. So there are two different types of crust. There's continental crust, which is thick accumulations of various rocks which are rich in aluminum and silica. And then there's oceanic crust, and that consists of thinner accumulations of basaltic rocks rich in magnesium and iron. So if we look down here at this image, we see that land, the hard crust that underlies the land, is called continental crust, and that the ocean is on is called oceanic crust. So where the continental crust meets the oceanic crust is the continental margin. Okay. So continental rocks are less dense than oceanic basalts, which means that our continents sit higher on the mantle than our oceanic crust does. Okay, and we'll talk a little bit more about that when we talk about plate tectonics in the third lecture you should be watching this week. Okay, so the continents sit higher on the upper mantle than expected due to their low density. So they rise up higher, right, than you would expect based on the thickness of that crust. Okay, so when we're talking about different areas of our ocean, we need to understand that those different areas are designated based on the depth. All right, so bathymetry is the measure of ocean depths and the charting of the shape or topography of the sea floor. So that can be done oftentimes using echo sounders. So this ship in this image is equipped with probably multiple echo sounders. And they essentially just drive over the ocean and they can get a map of the seafloor. So we've used these maps to understand the topography of the seafloor and to locate special features along the seafloor that are interesting to us for multiple reasons. Chemical reasons, geological reasons, biological reasons, and physical reasons as well. So all of the branches of oceanography would be interested in different features along the seafloor. So bathymetry is very important for our understanding of different branches of oceanography. So here's an example of a bathymetric image. So we have San Francisco right here, right, in Golden Gate Bridge, and there's Marin over here, and we have San Francisco Bay going in. All right, so the bathymetric image is showing you the entrance to San Francisco Bay. The legend over here on the right is showing you what the colors represent. So the shallower areas would be in the like light pinkish color, and the deeper areas are in purple. Okay, so take a minute to look at that to understand what this bathymetric image is showing us as far as the depth of the water entering into San Francisco Bay. So one thing that you should see is that the shallowest areas are where you would expect them to be. They are along the shoreline, and the deepest area is right underneath the Golden Gate Bridge. Okay, so as far as this is concerned, our entrance into San Francisco Bay, the deepest would be in the center, right? The shallowest would be closest to the land. And as far as the shallowest areas in the oceans are concerned, they are closest to the land, of course. But the deepest areas in the ocean are not necessarily in the center. In fact, the majority of the time, they're not actually in the center of the oceans, which we'll learn about a little more today. So there are 3 different marine provinces based on the depth and their location in the ocean. So we've got the continental margins, so that's the connection between the land and the sea. And the continental margins make up about 21% of the oceans. They are made up of continental crust with sediments on top. Then we have the deep ocean basin. So the deep ocean basins are between the continental margins and our next province, which are mid-ocean ridges. So the deep ocean basins are areas in the ocean that are generally deeper than 4 kilometers. And they are made up of oceanic crust with sediment on top. And then finally, we have ocean ridges. Ocean ridges or rises are raised portions of the seafloor that surround an area where you have continental or oceanic crust moving away from itself, or a divergent zone. And that's going to make more sense to you when we talk about plate tectonics. So oceanic ridges are made up of oceanic crust with sediments on top. Okay, so let's first talk about continental margins in a little more detail. So this image right here is showing you land over on the left, and then we have ocean right here. So here's the water level, or actually, sorry, this is the water level right here. So this is the shoreline, and we have the continental margin being basically this, from this area where the water comes up all the way out to here. Okay, so the majority of the continental margin is over continental crust, but it does make that connection to the oceanic crust as well. So we have the continental shelf, which is the submerged upper part, and it's usually gently sloping, but it depends on where in the world you are. That continental shelf could actually break off really quickly and actually be very strongly sloped. Then we have the shelf break, which is where the continental shelf suddenly drops off. And where it's dropping off, where the slope has increased, we call that the continental slope. And then down below the continental slope, you have the continental rise. This is where basically sediments accumulate there, and so now we have a very gently sloping seafloor beyond the continental shelf and the continental slope. This continental rise does not always exist because sometimes there could be a trench that's right off the shoreline. So you would have a continental shelf break, and then the continental slope would just continue down into very deep water. So you wouldn't have this gently sloping area. Okay, and an interesting feature that exists around our world in different places along continental margins are submarine canyons. So this image here is showing you a submarine canyon that exists in Monterey Bay, California. Or Monterey, yeah. Monterey is down here, Santa Cruz is up here, and the Monterey Canyon basically starts out right at the center of Monterey Bay. And this is essentially like an underwater Grand Canyon. So it's 470 kilometers long, 12 kilometers wide, 3,600 meters deep, and it has a relief of 1,700 meters. What that means is that's the difference between the continental shelf and the deepest parts of the canyon. Okay, so a relief of 1,700 meters is pretty big. Okay, so there are basically a whole community of organisms that exist, and it's kind of cool. The submarine canyon is kind of cool because scientists can study deep ocean right off of the beach. Basically, they don't have to go very far to get into really deep water. And the way that these submarine canyons are formed is basically due to currents, but there are special kinds of currents that are called turbidity currents. So a regular current would just be a mass of moving water, all moving in the same direction. Turbidity current is that moving water with sediment in it. Okay, so you can imagine like if water is flowing through sediment, it's going to carve out the sediment. And it also, it has a tendency to carve out harder rocks and everything. Now, if you add in tiny pieces of rock, then it has an even greater capacity to carve that out. And so that's what scientists believe have created our submarine canyons around the world, these turbidity currents. Okay, now our next region is the deep ocean basin. So the deep ocean basin, shown in this image, we have abyssal plains. So these are flat, deep regions of the ocean. There could also be seamounts, and there could also be oceanic trenches as well. Okay, so the abyssal plains, again, are the deep, flat region below the continental rise. And they usually are between 4 and 6 kilometers deep. And so in this little image here, what we're looking at is the sea floor. So this is only a snapshot of basically the deep sea. So we're looking at the sea floor. The abyssal plain is a long, flat region, and lots of times you'll have little hills, which we call abyssal hills. There are also volcanic peaks along deep ocean basins in places where you have heat seeping out from deep in the earth. So we call these volcanic peaks either seamounts, table mounts, or islands if they've risen high enough to break the surface of the water. So a seamount is generally a volcanic peak underwater that is continuing to grow. A table mount tends to be one that grew and it's no longer growing, and so it's kind of flattened out on the top. And then an island is obviously a seamount that has reached the surface of the water. And then also in some deep ocean basins you have ocean trenches. So an ocean trench is a deep scar found on an abyssal plain or descending from the continental slope due to convergence or collision between two oceanic crusts, or oceanic crust and continental crust. Now that'll make more sense again when we talk about plate tectonics and we talk about the movement of the crust, of the oceanic crust and of the continental crust around the world. And then finally we have ocean ridges. Ocean ridges cover about 23% of Earth's surface. On average, they are 2.5 kilometers above the surrounding seafloor, and they're made up of a rift valley, lots of volcanic flow, hydrothermal vents, and fractures and faults, excuse me. So this image right here is showing you an oceanic ridge. This is an ocean right here, right? Which ocean is that? We have North America, South America, Africa, Europe over here. So what ocean do you think that is? That is the Atlantic Ocean. I hope that that's what you guessed. So the ocean ridge right here is called the Mid-Atlantic Ridge. It runs the length of the Atlantic Ocean. So it's essentially like an underwater mountain chain. So one part of the ridge is the Rift Valley. So the ridge is created when you have heat coming up from deep in the earth and essentially causing new material to accumulate here. Basically, it comes up and it gets into the cool lithosphere, right, and it hardens. And so as it hardens, more and more and more of it grows, and so it ends up pushing the other crust over. And so that's why we call that a divergent zone. So mid-ocean ridges are divergent zones. And so as that happens, a little rift gets created at the very center of the ridge. We also see a lot of volcanic activity along mid-ocean ridges, just basically because mid-ocean ridges are areas where you have heat coming out from the ocean. So we have lava, essentially, that's coming up underwater, and when it gets into very cold waters, it hardens very rapidly, and it creates kind of a smooth texture, which we call pillow lava. So these are images of pillow lava, hardened rock that's smooth. We also see seamounts surrounding mid-ocean ridges, and that's because lots of times, this is the main point where the heat is coming up, but heat can also come up anywhere close by that as well. And so we often see volcanic seamounts coming up, and those volcanic seamounts can eventually keep on growing and growing and growing until they reach the surface of the water, and then we will call them islands. Another feature that are seen around ridges are hydrothermal vents. So there are generally three types of hydrothermal vents. We have warm water vents, which are below 30 degrees Celsius, and the water that comes out of them is generally just clear water. Then we have white smokers that are between 30 and 350 degrees Celsius, and the water that comes out of them is white, and that's why we call them white smokers, because underwater it looks like white smoke, but really all that it is the minerals are coming out of solution. There are basically minerals that are hardening as the water comes up, and so you're seeing those hardened minerals. And then black smokers are above 350 degrees Celsius, and they emit black water. So again, they look like black smoke coming up from a chimney. And so again, what you're seeing is not smoke, you're seeing just water coming up, and as that water, which was warm until it hit the surrounding water, once it hits the surrounding water, it cools, and so you have all of the minerals in it hardening out, and so you're seeing the hardening of that mineral. Previously it was dissolved into the water, and now it's come out of solution. So how do hydrothermal vents form? Essentially, there's a heat source, right, that ends up being closer to the surface of the seafloor in places that are surrounding mid-ocean ridges. And so, or there are other places as well that are called hot spots, which we'll talk about when we talk about plate tectonics. So if there's a heat source, then that allows for any water that seeps down into the sediment and into the crust to get warmed up, because the seafloor is hotter, right? So as that water seeps into it, it warms up, and as it warms up, it takes on the ability to dissolve more minerals. So essentially, like the minerals that are in the seafloor are dissolving into the water. Eventually that water comes back up, and as it does, it hits the cold water surrounding it. And so those minerals that dissolved now harden back up again. And so that's what we're seeing when we're looking at this formation here. This is just the hardened minerals that have come back and hardened, right? They were dissolved in the water and then they've hardened. And the black that we're seeing is that exact thing happening. The minerals are hardening before they were dissolved in the water, but once the water gets into very cold surrounding water, those minerals can't stay in the solution anymore. So they harden. Okay, and this is showing you the distribution of hydrothermal vent fields. The majority of hydrothermal vent fields are found around ridges. So here we have the Mid-Atlantic Ridge, and you can see lots of vent fields over there. Then we have the East Pacific Rise, which is another type of ridge, but it's called a rise, and I'll talk about why that is in a future lecture. And then you just basically follow this black line around. That's all ridge. Okay, so you see the majority of vent fields, of hydrothermal vent fields, are around ridges, but there are some exceptions, and those are usually due to hotspots. Okay, so that's it for this lecture. If you have questions, please post them under the weekly discussion, week 3, and you'll have 4 additional lecture videos for this week. So make sure that you come up with a question for at least one of those videos. Okay? Thank you. I hope you guys are having a good day.